Hello everyone. In this video, I'm going to demonstrate the y86 sequential processor on the fetch, decode, and execution unit. Okay, let's get started. So for this demonstration, I'm going to use the test program on the right-hand side. Okay, so this program includes all the instructions we are going to implement. Like all the data move instruction, IR, RM, MR instructions, and then also RR move instructions here. Also, it has 4 arithmetic operations as well. Okay, so but we don't have a jump instruction, right? So I will use jump instruction after we implement what's that? The data memory write stage, which is the uh, next stage. Okay. Using this program, we are going to test the circuit on the left-hand side, and it is getting complicated, right? But it's exactly same with the y86 hardware structure we are following. Okay, so around here, this is the fetch unit, and here we have a decoding unit and write back unit. So it is both decode and write back stage, and then here we have a execution unit. Okay, so later we will have a data memory here, and then we are done. Okay, so actually on top we have PC update stage, but still it is simple, right? Like I mentioned, just VLC, which is one of the candidates of next PC, will be used for next piece because we have only one candidate for now. So we will focus on fetch, decode, write back, and execution stage here. Okay, let me drag it a little bit more down for you to see all of them together. Okay, good. Here, before we start actually running this program, let me introduce one important concept, which is the clock system, and then recall previous demonstration and tutorial. So I just uh, clicked this clock 6 times so that we fetch a single instruction, right? Because the maximum size of instruction is 6 bytes. So in my design, I uh, need 6 cycles to fetch 6 bytes. Okay, so after 6 cycles, all the I code, iPhone, RA, RB, VLC, and 2 signals here, and what's that? All the source and destination register IDs are available, right? Because there is no other what's that other unit which has a storage. Okay, what I'm saying is, so until here, 6 cycle, oops, 6 cycle, in 6 cycle everything is finished. Okay, after 6 cycles we get entire instruction, and then we get this information. We can read register IDs in the second cycle because register numbers are stored in the byte 2, second byte. So after 2 cycles, we read, what's that? This source and destination register IDs in the next cycle. In the third cycle, register file can give us the data or can store the data, right? But the problem is when we attach execution unit, see? So execution unit needs to wait 6 cycles, and then at 7 cycle. At 7 cycle, let's say cycle 7, it can execute and produce correct data, right? Which means register file or decoding stage needs to or can write the computed value back to register, right? Or the data register file wants to store is available after cycle 7 because at cycle 7 data will be generated, right? So for example, IR move instruction with V and RB. This is the format of IR move L instruction, right? So this V, let me clear let me clear and draw again. So IR move L instruction, for example. So val C comes from instruction itself, but it does not go to the register file directly, right? It goes to the ALU first, and then ALU just forward this value to the register file, this path, right? Okay, based on this, then so we need after 6 cycles, ALU can get the value C, right? And then at 7 cycle, ALU can start outputting this value C, right? And then at cycle 8, register file can store the incoming data to the corresponding register, okay? So then, so this is a sequential processor. So until everything is done, okay, until one instruction is completed, we cannot start next instruction, okay? Which means fetch unit needs to wait 2 more cycles to fetch the next instruction, okay? So then, in short, to complete entire, to complete one single instruction, we need 8 cycles in total, okay? So then after, then at cycle 9, fetch unit needs to start fetching, okay? So then we need 8 cycles, let's say 0, 1, 2, 3, 4, 5, 6, 7. And then until for the first 6 cycle, fetch unit actually works. And then fetch instruction. And then next cycle, cycle 6 or 7th cycle, execution unit actually works with valid inputs. And then next cycle, write back stage actually works. Then where is decoding unit? Actually, decoding unit starts working where from the second cycle 1. Right. Also, this write back is part of decoding unit, but the writing back should happen at cycle 7 or 8th cycle. Why? Because execution unit produces the data for write back. Okay, so this is kind of challenging part for you to work all together, work these all components all together. Okay, and also this cycle information works for only this version. Okay, so what I'm saying is if we put another stage, which is memory stage, we need to calculate this cycle timing differently, because that needs, so for example, write back stage. So here we just assumed data is coming from execution unit. But what if data coming from the memory? It is possible, right? When we want to move data from memory to register, then we also need to consider this timing as well. But we will talk about that final timing in the last week, week 3. Okay. But yeah, so keep this in mind when you implement and put all together. Okay, then again, for each module, like fetch unit, decoding unit, decoding and write back unit, and ALU unit should know when to start execution. Okay, so fetch unit starts first cycle. Let's say this is the one big cycle. This is the 8 cycles. So this processor executes one instruction or completes one instruction for every cycles. And then what is the timing of fetch unit starts? Cycle 0. And what about register? Second cycle or cycle 1 for reading, and what's that? Cycle 7 or 8th cycle for writing. And what about ALU? ALU can start execution at cycle 6 or 7th cycle. Okay, so inside in each module, you need to have extra logic to control this timing. Okay, otherwise, this each unit will take wrong input and then produce some wrong output. Okay. Okay, good. I think this is good enough for this timing. And then I'm going to execute maybe first 1, 2, 3, 4, 5, 6. Yeah, 6 or 7 instructions. Let's see. And then I'm going to highlight. I'm going to fetch. I'm going to click one by one and then show you how data. I'm going to show you the data movement. Okay, so it will be good for you to understand data path you are going to learn in the lecture as well. Okay, good. So since the machine code is hard to see, so I'm going to write the machine code on the black screen. The first instruction is 30 F0 0F 000000. Is it correct? 30 F0 0F. Okay, good. Then let's get started. Reset the signal. Okay. By the way, we see some error line here. Okay, but actually we don't want to have any error at any point of time. But there is some circuit too much detail. So in this project, it is okay before and after process entire execution. Okay, so once you start clicking, you shouldn't have this. And I mean for between cycle 0 to 8, we don't want to see any. We can have a red line, but after 8 cycle, or for every after 8 cycle, we don't want to see any error line. Okay, even inside each modules, right? But during 8 cycles or before start program running, it is fine. Okay, let's click first. Okay, I clicked once, and then so here to see how many cycles we clicked, I just attached counter over here. So maybe you can see how many cycles we clicked so far. Okay, so we clicked first, we clicked once, and then oops, machine codes are gone. 30 F0 0F 000000. So we read first byte, and then it is I code and iPhone. So we see I code and iPhone. Okay, it is correct. And then I'm going to draw data path as well. Okay, then it goes let's draw I code first. It goes everywhere it can go. This, and this, and this, and where else? I think this is it. Okay. I think this is too much. Okay, let's not do it. Okay. Anyway, we checked that we got I code 3 and I function 0, which is good. And then let's click second. Okay. We fetched second byte F0. Where is it? It goes to RA and RB. RA is F, which means we don't want to read RA. And then RB is 0, which is maybe y86 register. Okay. And then what is, so based on I code, we can calculate IR, we can write IR move L instruction. And then after read next byte, we write RB, which is EAX. Okay, good. And then next, we need to read value C, constant value. So then let's click 4 times to read 4 bytes. 1, 2, 3, 4. Okay, good. After 4 cycles, we get value C here. This is what? 0x 0 0 0 F. Okay, good. So then after we read 6 cycles, then we can check whether register file actually produces correct value A and value B. Okay, so here we want to read. There's nothing we want to read. Okay, so source B and A must be F. Okay, And then what about destination? So we need to set a destination, right? And the actually destination data is coming from E. So RB, so RB, which is ID 0 will be go to destination E. Okay, good, which is 0, and it goes to this way, and then selected by this E module, and then actually going to this input ports. And then we are waiting the data from execution unit, this one. Okay. And then the data from memory is not connected yet because we didn't implement it yet. Okay, good. So we clicked 6 times here. Uh, we clicked 6 times. So this is actually cycle at 6, and then next is 7 cycles. Okay, then after next cycle, or so then okay, before click it, then ALU actually is ready to execute, which means all the data, input data for ALU is ready. Okay, so then let's check the input data and signal of ALU. Okay, so here so let's check ALU A and B first, and then you can see actual value of 2 data inputs on the left side. Okay, so ALU A is F and ALU B is 0. Is it correct? Yes. Right. So why? Because we want to just forward value C, and then finally it goes to the register. Okay, in this case, we want to do just 0. We want to just do val C plus 0. Okay, then we take val C, which is F, hexa number F, and then val B is 0. And then what about ALU function, which is 0? It is addition. Okay, good. And also here set CC produces 0 value. Why? Because it is non-arithmetic operation, or it is non-OPL instruction, which means we don't want to store condition code. Okay. Okay. So then I think we are ready. The data are ready and correct values. Okay. So then after next cycle, we expect that the value output, so this line out will present the value F, right? So let's click it now. Okay. Click, okay, done. All right, so on the right, on the wire value E has the value F, right? Okay, then data, the value F is going to register file, but register is not, this value is not stored this moment, at this moment, right? It will be stored in the next cycle, right? Okay, then we can click once or once. This is the last cycle. Okay, click. Okay, so so far we don't see we cannot check whether it is stored or not. I can check, but since I don't want to show you inside detail, so but it is stored. Here, notice that at the last cycle, this PC was updated with correct value, which is 6, right? 6 is the next address, here next address where the next instruction is stored. Okay. All right. So far so good. We finished what first instruction using 8 cycle, right? Okay. Good. Okay. Next instruction. It is same. So let me quickly write move L with not this one. Machine code 30 F301 FF. Okay, but for this instruction, since it is same instruction, I'm not going to clock. Clock by clock, cycle by cycle details. But let's just decode it and then guess what is the values after 8 cycles. Okay, so this is 30 means 3 means IR move instruction, and then 0 means so iPhone is 0 definitely, and F means we don't want to read RA register, and then next we want to read RB register, which is EBX register. Okay, and then next 4 byte is constant value, immediate value, but it is written as a little endian. So the value will be 00000001. Let me write hexa number. Oh, this is hexa number, but use just 0, 1, 0x01. Okay. And then after 8 cycles, let's say we want to see the value E, which is 0x01 on this case. And also, what about here? Source 1 and source A and B should be 1111 F 1111 F, and then destination M also 1111, but destination E will be 0011. Okay, and then yeah, I think this is good enough. Let's do it. Let's click 6 times. Sorry, 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. Great. This is correct. And then these are correct. Great. And also you can check whether others are correct or not. Okay. I let you check, so it is correct. Okay. Good. Let's move on to the next instruction. So now we have arithmetic instruction ADDL. Okay. And this is just 2 byte. 060 and 03. Okay, but note that even though it is 2 byte long instruction, this machine just fetch 6 bytes, and then the other 4 bytes won't be used. Okay, but since it is first instruction, I'll show you cycle by cycle details. Okay, so let's click once, and then we got I code, which is 6. Okay, good. Here we got 6. So then we know, okay, I code 6 is OPL instruction, but since I fun is 0, we know it is add instruction. Okay, ADDL instruction. Okay, so let's click one more. Then we read 03, and then first digit is RAID, which is y86, and then what's that? Next, 3 is RB, register BID, which is EBX. Okay, good. We decoded. And then we just click 4 times. 1, 2, 3, 4, and then so we got something on here, but we are not going to use this value. Okay, good. And then what about source registers, source and destination registers in the decoding stage? Okay, so here we want to read both RA and RB, so this is updated correctly, 0 and 3. And what about destination N, right? The data is coming from the execution unit, and then this data is going to RB register, which is 3. So dest E is 3 and dest M is 0. Okay, perfect. Good. Actually, and yeah, val P is updated correctly, which is the next instruction address. Okay, so then ALU is ready to execute because data is available. So then let's check inputs of ALU first. Okay, here let's check ALU and ALU A and ALU B. Okay, so then so you remember that so in the previous 2 instructions we assigned F to EAX and 1 to EBX. So EAX has value 0xF, and then EBX has value 0x1. Okay, so then when you see the ALU A and ALU B, it has correct value F and 1. Okay, so then this is ready, and then what about okay, sorry. What about ALU fund? What is the operation, exact operation we want to do? Addition. So I fund is 0, correct. And this set CC produce value 1, which means we want to store condition code. It's correct because it is OPL instruction, right? Okay, good. But we didn't actually execute this instruction yet. Okay, so in the next cycle, ALU will execute and then produce the outputs. Okay. Then what is the expected output? Let me use different color. So since it is addition, so 0x plus 0x1 is 0x10, right? So we expect value 0x10 on the line, on the wire ALU E, sorry, on the line val E, okay? And then what about condition code? Okay, so we have a 3-bit condition code. So first bit is like 0 flag and sign flag and overflow. Okay, but here this is not 0 and this sign this is positive value and there's no overflow, so we will get 0, 0, 0 as a condition code. Okay, let's click the cycle. Okay, good. We got the correct value 1, 0, and also we got the correct condition code 0, 0, 0. Okay, so then data is coming to CC and register file this way, but it's not stored yet. It will be stored in the next cycle, right? So then let's click once again. Okay. Then after that, what's that? The PC value is updated, okay? And then ready to be executed next cycle. Okay, we are done. Okay, and then next 3 cycles are all what's that? OPL instructions. So I'll just click 8 times and then get the correct, check the output value after that. Okay, so let me, so then let me write next instruction, which is, machine code is 6103. Okay, let's decode it ourselves. So 6 is OPL instruction, and we should see I1, which is 1, and it is actually subtraction. So we write sub L, and then next byte has RA and RB ID. So 0 is what? EAX, and 3 is EBX. Okay, we want subtract EAX and EAB, sorry, EBX, and then write back the result to the EBX. Okay, so then do you remember the value of EAX and EBX? Okay, so EBX actually has 0x10, and then EAX has value what? Uh, F, just F. Okay. Yeah, so we stored value F to the EAX in the first instruction, right? IR move instruction. Okay. Then it is 0xF minus 0x10. Then what is um, the result? This is a -1 in decimal, but value we use 2's complement. So the value will be actual value will be 1111. Okay, let me use hexagon notation. Okay. F F F F F F F F. Okay. This is the two's complement of -1 using the two's complement. Okay, this is the expected value on value E, right? And then what else we want to check? Maybe we can just, I think, yeah, let's check just output value, then it is good. Okay, then I'm going to click 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. Okay, we have a correct value, all ones. Oh, we need to check one more, which is CC value. Okay, now CC value is 010. Is it correct? Yes. So second bit is actually sign bit. So when it is set, when sign bit is set, when the output is negative value. And this is -1, so sign bit is set. Okay, it is correct. Good. And then next, what is the next instruction, which is 6203. And let's decode it. And then 6 is OPL instruction, and we should see I function, which is 2. Then it is AND operation, and L, and then register. Next is register. 0 is EAX, and 3 is EBX. Okay, good. So you remember the EBX stored the previous output, which is FFF -1, 0x, F, 1, 2, 3, 4, 5, 6, 7, 8. This is -1. And then EAX. We didn't change EAX, so still we have 0xF in EAX. And then the operation is AND, so AND. Okay. Then what is the output? Output would be just 0xF. Or you can also write 0, 0, 0, 0, 0, 0, 0, F. 1, 2, 3, 4, 5, 6, 7. Okay. These are equivalent, but the why we put leading zeros? because with leading zeros, we know exact bits used in the hardware. Okay, hardware is fixed one. So actually, even though we skip leading zeros, we should imagine there are leading zeros in the hardware. Okay, this is the output of output in the on the VLC. This is 0 x just f. Okay, and then what about CC value? Okay, so then CC value, like this is non-zero, so we will get 0, and this is not positive value, so it's still 0, next 0, and then there is no overflow, 0. Okay, so we calculate it to expected value after 8 cycles. Okay, let's go. 1, 2, 3, 4, 5, 6, 7, 8. Okay, done. All right, so we got the correct value, 0x f, and then we got also correct value on the condition code. Okay, we are done. And then let's do the last OPL code. Where is it? Okay, Z6303. Okay, let's quickly decode. So this is 6 is OPL code, then iPhone 3 is XOR, and then okay, so register names same. So EAX, EBX. So you remember the result, previous result was stored in EBX, which is just 0xf. And then still we have a value, oops, 0xf in the EAX. Okay, and then what is operation? XOR. Maybe a head in the C code. Okay, then what is the output? 0, just 0, because we are XORing two same values, then it is 0. Okay, this is the val E value, and then what is the condition code? So this is 0, then we get 1 for 0 flag, and this is positive value, just 0, and then no overflow, 0. Okay, so then 0, 0, 1, and 0x, 0. Let's click 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. So we got 0, and we don't see this value. Okay. We got 0, 0, 1. Correct. Okay, we are done with OPL instructions. Okay, let me do last one, RR move instruction. And actually here you see two more instructions, which is RM and MR instruction. But I'll leave this instruction for you. You can debug yourself or demonstrate yourself. Okay, but let me do the last instruction, which is 0, 2, 0, 0, 1. Okay, then let's decode. So let me do it one by one, one cycle by cycle, since it is new instruction. So let's click once. Okay, so we got I code 2, iPhone 0. Okay, here. Then I code 2 is actually RR move L instruction, and then next cycle click, then we got RA0 and RB1. Okay, but okay, since it is R register to register move, so we need to read, we need to then we can write RA, which is EAX, And then 1. What is 1? What is the register ID 1? It is actually ECX. Okay. And then, so we clicked second, and then, but even though it is 2-byte long instruction, we need to click 4 more times. 1, 2, 3, 4. Okay. Then we can check input to the register file. Okay. So since so we need to read RA register, which is 00. So source A should be 0000, but we don't want to read RB. We want to write something to RB. Okay, so source B is FFFF, and then data is coming from the execution unit. So, and what is the destination? ECX, which is 1. Okay, it is correct. And then destination M, we don't get data from this memory, so it is 1111. Okay, decoding is correct. And then what about the values? Okay, yeah. So then EAX actually has value what? 0xf. Okay, so you see the 0xf on the val A side. And then I think we are ready to execute ALU. So then we, before that, let's check the inputs to ALU first. Okay, so sorry. We should, so here we want to forward this the RA value, F0xf. Okay, so ALU should be value A, which is 0f, correct? But what about ALUB? We just want to forward ALUA or value A. So ALUB should be just 0. And then we are going to use addition operation. Okay, so that we just forward it. And then after execution, expected val E be just F. Okay. Okay, good. So then what about a CC code? So current CC code is still 001. Okay. Note that even though we execute non OPL instructions, we should keep this value. Okay. And then, okay, then let's click once. Okay, great. So val E has correct value F, and CC value still 001. Okay, even though ALU output CC value 000, this CC module still stores the previous last condition code. Okay, good. And then in the next cycle, the value F on the wire val E will be stored in the register file. Click. But we don't see the value, but yeah, it is stored. Okay. I think this is it. And yeah, so with execution unit, you can see some arithmetic operation, computation, and how it is working, and then how it is stored back to the register. Okay, so in the next week, we are going to implement memory, and then we can actually complete the instruction for RM and MR instruction. And then also using this condition code, using this condition code, we can finally implement jump instruction, or we can execute jump instruction, right? So far we just used val p for the next PC, but later, next, like we can decide val C, which stores destination, or val P, which is just next address of the next instruction. So we can select this val P or val C using this condition code if we are executing the jump instruction. And where it is this decision making is happening, it is happening in the update PC stage, like here. So we will finish this update stage in the last week, week 3. Okay. Thank you for watching this long demonstration, and um, um, all the best. And let's see. I will see you on the lab. Yeah, bye.